Or Bell Ringer was the birthday song today. I'm fine with that. Yep, I forget about it. Cool. All right. We are so close to being able to do logarithms, which I'm excited for. I can tell you're excited for. But what we're going to wind up seeing is this formula, P e to the RT, it gets used everywhere. It works really well with money if money is done continuously like this. It works much better in the world of physics and chemistry and stuff because banks, if they can save $2 per person and they have 10 million customers, of course they're going to do it, right? Like, why would they not save $20 million? Turns out the universe doesn't really care about that sort of thing. If I had a big piece of plutonium in here, do you guys know what plutonium is? Is it an actinide or a lanthanide? I think it's an actinide. I think it's 94. I think it's an actinide. Okay. Anyway, doesn't matter. Let's use a better one. In cartoons. If I were, let's say that I just got off work at my job at the nuclear power plant where we use plutonium 239 as our fuel. And I said, gosh, you know what? I know this group of kids that live around here and I teach them that would love to see this. And I brought in a big old chunk of, we'll use uranium because it's easier to think about. And I said, guys, check this out. And I said a big chunk of enriched uranium right here. You cool with it or no?
No.
Why? What does that mean?
It decays and it sends out the energy, and then we get the energy.
Okay. How many of you guys know what Karina's talking about there? It decays and it sends out the energy. Okay. So check it out. When we talk about decay, your mind and my mind probably. Am I recording? Yeah. Okay. I can tell. Your mind and my mind probably go to the same spot. I think of food is what I think of because decay and rotting. I might think of a log in the forest, or it's more graphic. I try not to think of dead bodies, but decay, right? Like stuff decays. Now, it turns out elements also do that, but it's very different. If we had a dead animal, whatever it is, and it decayed, eventually it's just gone, right? Now, that is one type of decay, that's biological decay. When we talk about radioactive decay, which is what we're going to talk about today, what winds up happening is you have these elements, these atoms, right? Atoms are made of what again? So you went way further than I was expecting. Quarks? How many types of quarks if we're going down this road? Up, down, strange. Not Riz, but
Up, down, strange, charisma.
charm, but yeah.
What are the other two?
Top, 6. Top,
Bottom.
bottom. Okay, so before we continue on, here's my question. You guys were talking about atoms and stuff. The only reason I'm connecting it to the chemistry. Have you talked about quarks in there? Or is it just something you know?
No.
Okay, so let's not use the standard model. What is every atom made of? 3 things. Protons, neutrons, and electrons. Okay, you guys have been talking about that at least in some fashion. What's in the middle? And what is, right? So the nucleus, I'm cool with that. And we could call these nucleons because they live in the nucleus. What are the 2 types of subatomic particles that are in the nucleus of an atom? Protons and neutrons. Which one's positive? And a neutron is, and then out and about somewhere is the electron. And you never, depending on the model that you guys are talking about, I don't want to say too much about it, but it gets weird. Like, it does get weird, and it gets awesomely weird. Okay, as we're looking at this, some things are stable, right? Like whether it's an element or a desk, like we have this idea of stability. If this is not perfectly stable and like I started shaking it, eventually what's going to happen if it's not stable? It's going to break and fall apart, right? And we'll see little pieces shoot off of it. Same thing happens with atoms, and it only happens with certain types of atoms, and this is called radioactivity. Now, radiation can be dangerous, but it doesn't have to be. If I said, I'm going to blast you all with radiation, you're probably pretty uncomfortable with that. But check it out. You are being blasted with radiation right now. There's light coming out of this. That is radiation. It's on the electromagnetic spectrum. Turns out it's visible light, and it's not dangerous to us. Now, the sun, we use its light all the time. We need its light. But me, probably more than almost anybody in here, if I spend a lot of time out in the sun, I burn, baby, burn, for sure. Why? It's UV light. Can you guys see UV light? No, but it's there. Now, it's also in the electromagnetic spectrum. It just has a bit more energy than the other stuff. Okay, if I have cancer in the middle of my brain and they can't cut it out because, my brain is there, how do they get rid of a tumor on the inside of me? You use radiation therapy. Now, if you, unfortunately, probably all of us do, know somebody that has undergone cancer treatments, they are awful, just in general. But it's like in 500 years, they're going to look at us and be like, what the hell were they doing? Like, it's going to be wonky because there's really two major treatments to cancer these days. You can either poison the crap out of somebody and hope that you poison the cancer enough to kill it while poisoning the person not enough to kill them. That's called chemotherapy. You're literally just poisoning them, which it sucks, but it poisons the cancer faster than it poisons your living self, and the cancer eventually, hopefully, dies. Sometimes that works. It doesn't all the time. The other most common treatment is radiation therapy. Now, anybody here ever had an x-ray? Okay, when you have an x-ray, does everybody just kind of hang out and nobody worries about it? Or do you have to put on special clothes? They put something really heavy on you. What is it? It's lead. It is lead. It is a lead apron. Now, lead is terrible for you if you were to eat it or get it into your body. But the good news is in an apron, like solid lead itself isn't dangerous. Lead pipes themselves aren't dangerous until they start leaking stuff. Like that's where the lead issue comes in. Why do they put lead on you? Yeah, lead is really, really dense and the radiation can't get through it. Like have you guys ever known how an x-ray actually works? So there's radiation blasting out of the machine. It's in the form of x-rays. It's a type of electromagnetic radiation. And the particles that shoot out of it, you can't see because they're too small. Just like you can't see the photons that carry light here. Like we see the ultimate, like all the light put together, but you can't see one piece of light shooting. Like we can't. The same thing happens. It's invisible. And it turns out the stuff in x-rays is strong enough that it shoots through your soft tissues. It goes all the way through your body and hits the screen behind it. They have that plate there. And when it hits that plate behind it, it leaves a little mark. And it's just, we're seeing contrasted stuff. Okay, what's easier to pass through? If I shoot an arrow through this part of my thumb and it goes through all the tissue, like if I have a blow dart, could it go through? Yeah, conceivably. What if I did it right through this bone? It's probably not going to go through, right? That's how an x-ray works. It doesn't go through the bone quite enough because it just doesn't pass through and then leave the mark on the plate. That's what x-rays are doing. They're blasting stuff through your body. Right now, you can't feel it. Billions and billions of particles right now are blasting through each and every one of us all the time. They're called neutrinos. They are small enough and light enough and fast enough that they don't really interact with any part of us, which is why they're so stinking hard to detect. But they do exist, and they're passing through you right now. You don't feel it. They're not dangerous. Now, you don't really feel an x-ray either, right? Like, sure, you feel some things if you're getting an x-ray, you're in pain, but it's working through that radiation. Now, x-rays are kind of scary. They're not scary enough that you would worry about getting a singular x-ray ever. But if your whole job all day, every day is to run a machine that shoots out x-rays all over the place, when they do an x-ray on you, where do they go? They go behind the counter, right? Because one x-ray is not a big deal. 10 x-rays, realistically, is not a big deal. But if you're given hundreds and hundreds of x-rays every single day, big deal. Now, we can get more powerful. Other types of electromagnetic, and it feels like science, which it is, because we're just building up to it. Hopefully you're learning something right now. Okay, we can get more energetic than x-rays. And there's these things called gamma rays. If the world ends when I'm alive, I hope it ends in a gamma ray burst. Now, I'm not saying I want the world to end. Don't misinterpret this. But there's things out there way more powerful than the Earth, way more powerful than the sun in our universe, right? Give me something bigger and stronger than our sun. Black hole is a big one. Neutron stars, like there's way bigger stars. Our star, middle of the road, like realistically not that big. There's much larger stars. Eventually, and occasionally, and their universe is so large that this does happen, there's a few different ways. Stars eventually run out of gas, right? Not gas per se, but they run out of fuel, right? And if they don't have any fuel, but they still have all that mass in them, they collapse. And sometimes, eventually, they turn into a black hole, right? What's the process called of a star going from a star to dying and collapsing in on itself? It's a supernova. Now, if a star is here and it goes, a bunch of stuff shoots out, right? Okay, gamma rays are what wind up shooting out. And it turns out that very low chances, like almost zero, just so you guys are aware. The good news is, even if it did happen, we would never know that it happened. So take that with a grain of salt. Nobody would know. Nobody would be aware of it one bit. If that happens somewhere in the universe and it's close enough and pointing directly at our planet, just that's it. It's done. Like, it's done. Everything is done. Now, the good news is that that's unlikely to happen. The better news is that we actually take advantage of that. We use gamma ray bursts at a much smaller scale to take cancers out of the middle of people's brains. If I set my machine to turn up the energy just enough so that if I shoot it into my head, and we're just going to draw a bad picture of a head here. Did I show you guys White Ninja the other day?
Yeah.
Okay, so here's White Ninja. So here he is. And he's smiling. Okay, I don't know why he's smiling, because he's about to get a gamma ray burst to the brain. But here he is. Okay, so let's say that we're going to let this gamma ray blast in. If I turn it up too high, it does this. And I guess we can probably even add a little bit of dimension to this. It goes, and it shoots right out. That's too high. If I turn it down and it's going a little bit less energy, maybe it just won't go as far, right? Now, let's say on the inside of this guy, right here in the middle of his brain, is this tiny little tumor. And I want to be able to get it. There's a setting on this big, fancy, multi-million-dollar machine that I can turn it up just enough so that when it comes in, it goes and it loses energy and it only ends there, right? Like, I'm just changing how fast am I shooting it. That's really simplified down. But if I blast this thing that is going to get destroyed by the radiation that's right in the middle of my brain, I can do it without having to cut out all the other stuff around it. This is a form of cancer treatment, and it's all using radioactivity. Now, radiation can be scary, and you should be afraid of it in certain situations, but not normally. Most of the radiation that we deal with is light or radio waves. Like, they're blasting radiation out of KUCB over there. They're big, long waves like this that are traveling. We just can't see them. Okay. Now, all of this to say is that when radioactive stuff happens, there's a whole lot of it. We just did a bunch more science than I was anticipating. Hopefully, it's at least kind of interesting. Nobody fell asleep, so that's good. Okay, hit it.
We don't have enough radiation from our phones to actually affect this thing.
Seemingly no. I mean, long-term studies usually last longer than 20 years, which is about how long we've all carried these fancy things in our pockets. Seemingly no. Like, there doesn't seem to be a link. But I'm also not a doctor or a cell phone researcher or whoever would be dealing with that. Okay, now we're going to go back to that other idea that we started with plutonium and stuff. And Addison's going to watch this and be like, what the hell were they doing? Okay, if I put a big chunk of plutonium here or something radioactive that's really unstable, all it does is it just spits out little pieces. Now, it might be electrons that fly out. It might be some neutrons that fly out. Sometimes, depending on the type of radiation, some of the protons piece out. Now, when you think of decay, if this was a chunk of uranium and it started to decay, we're not going to see a whole lot change about it. What's going to happen is eventually it'll lose enough of its protons in each individual atom that it, instead of like decaying and disappearing like we see with other stuff, it just changes into a different material. So something with fewer protons. And I don't know what uranium or plutonium turned into off the top of my head, but let's say maybe it was uranium now, and then in 10 years or however long it takes, now it's a chunk of selenium or something. Just a different number of protons. Don't care what the actual element is, but it turns out that when it shoots that stuff out because it's decaying, some of that is bad, and some of it can be dangerous radiation. Now, two things with that. One, awful. Two, awesome. Because that fact that it does that is how nuclear energy works. It is disgusting that we as a planet don't use more nuclear energy than we do. Like, whatever, we're in Alaska, there's an emphasis on certain types of energy, and I'm not really saying that any are bad. But what I am saying is there's a good one that's really accessible, but we have a bad taste in our mouth because scary stories. Chernobyl is probably what you think of. Fukushima. There's some bad things that happen with it if you're not careful. Are there bad things that happen with every type of energy production? Why do we pick on the one that is almost free and does way more energy? I don't know. We should have more, in my opinion. That's my opinion, right? That's not a fact. I think we should have way more nuclear energy than we do, just for the record. Okay, with all that said, the decaying, it turns out that it happens semi-randomly. Like, we don't know for sure if something is going to decay at this particular point in time, but given enough time, on average, here's what it looks like. Okay, and that's like how it works. When we talk about this, you've probably, if you're into physicsy stuff, you've probably heard of Schrodinger and something about a cat that got murdered. Cool. All right. Or didn't, I'm not sure, or both, whatever the case might be. We're going to jump in on Schrodinger's shoulders here a little bit, and we're just going to see our last application. We did the money stuff, which is fine, and that one's much more relevant to your everyday lives, unless you're going to be a nuclear engineer, which I hope some of you are. That'd be awesome. In either case, we're all going to be nuclear scientists today because we're going to be talking about radioactive decay. What a cool intro. Yeah, but hopefully you learned something and you have a little bit more appreciation for the science and math connection. We're not in math class, we're in STEM class. All right, right off the bat, we have this idea that we're going to define that I think you guys have heard called half-life. Okay, whether you know exactly what it is, it's not a video game. I mean, it is a video game, but that's not what I'm talking about. Anybody recall hearing about half-life? You guys probably, you don't remember the word, or? Okay, so if you didn't take my physical science, you might not have ever seen the word. If you had my physical science, I'm pretty sure we talked about it at one point, but I don't recall. Maybe not. I'd have to look back at my notes. Okay, so Ms. Holloway then might have talked with you about it. Okay, half-life is an interesting idea. When you see stuff, most things have a half-life. And all that this is by definition, the amount of time, or I'm going to say the time needed, for 1/2 of a substance to decay. Now, this gets used in other places apart from like nuclear engineering stuff. If I were to take, I don't know, like a Tylenol or something, and my body dissolved it and it went all through my body, if I went to the clinic later and I said, test my blood to see if there's Tylenol, would they find some? Probably. Would they find some tomorrow still? Probably, but maybe not. I don't know how long it goes. Would they find some in my blood still 6 months from now? No. So, like, clearly my body gets rid of it somehow, right? And what ultimately happened is you wind up peeing most of it out because your kidneys would filter it out of your blood, and then you would pee it. But, lost my train of thought there, I'm sorry. Okay. At some point, was there half as much Tylenol in my body as initially was? Like, there must have been. If I went from full amount to none, I had to cross over half. And then once I'm at that half amount, is there another half amount where I now have half of that amount? And it keeps repeating, right? Every time to get to zero, we just cut in half over and over. That is the idea of half-life. Now, it turns out that with radiation, it's fairly consistent. And we're going to jump right in with this, and I will help us set it out. So, do you want a real problem or a made-up problem? A real problem. Okay, so here we are. We're going to do an example with half-life, and we're going to work this out. And we will see it again this chapter, just so you guys are aware. We're going to kind of do real. If you let me Google something, we could look and get real info. But 1986, Chernobyl. That's where we're hanging out right now. There's a wonderful miniseries on HBO called Chernobyl. Worth watching. I would recommend it. It's real good. Now, in a nuclear reactor, typically what's used is plutonium, and we're going to do a quick. So we're not going to use the real numbers because they're going to be too big. We'll say we're in 1986 Chernobyl, and just to set the scene, we are in a small research lab on campus somewhere at this nuclear power plant. And instead of working with 15 tons of this radioactive material, we are nuclear physicists, and we are working with a much smaller sample. So here we go. We have, hypothetically, let's say 10 pounds of, and I'm going to write this in a weird way, Pu 239 or 239 Pu. Now, this is just an isotope. That's all this means. Pu is the chemical symbol for plutonium, which is a radioactive actinide on the periodic table. It is actually not a natural occurring thing. We have to make it. We refine uranium and we can make plutonium. Now the 239, since you guys are talking about atoms and stuff, any idea what this is? Good. It's telling me the specific isotope. I know plutonium has a particular number of protons in it. That's what makes it plutonium. But we can change the number of neutrons, and it's still called plutonium. It's just called an isotope. Is this also what you're talking about? Okay, so sorry about that. So all that matters is that this is super radioactive and dangerous if not done carefully. Okay, here's what else we know. Looking at this, we have 10 pounds. I'm also told the half-life, which we're going to write the word here, but I'm going to teach you the Greek letter that we use to represent this. It gets wound up mixed with another one that is used for wavelength. Lambda is half-life. Looks like an upside down Y. I do this. Cool. The half, nope, can't erase it. Don't know why it does this. Can't even undo it. Sorry. See, watch, if I control Z, now it just starts undoing that stuff. Every once in a while, it gets crazy. So we'll just switch colors so we can see it. Okay. The half-life, lambda, of plutonium-239 is huge. And this is one of the arguments against nuclear energy. This is a rough approximation, equals 24,100 years. Okay. That means if I have 1 pound of it, or 10 pounds of it right now, if I wait 24,100 years and I see that rock and I see how much actual plutonium is in there, if there was 10 pounds of pure plutonium initially, half the amount is gone. I now have 5 pounds of plutonium. Now I still have a 10-pound rock, realistically, pretty much. I might lose a little bit with radiation, but I only have half as much plutonium. Go another 24,100 years and I'd be down to 2.5 pounds. And this is the issue, because when we have waste, typically we bury it. Like, that's, what do you do with it? You encase it in glass, and then you encase it in concrete, and then you encase it in lead, and lead, and lead, and then you bury it so deep that you hope no human will ever find it again. Or you dump it in the ocean. One of those two things. Wish I were kidding. It's happened. Oh yeah. Oh yeah. I mean, the Bikini Atolls, the atolls in the Pacific, we dropped so many nuclear weapons just willy-nilly when we were developing them. We've done it. Other countries have done it. Yep. There's likely radiation in the water. Not enough to be super dangerous for us. Probably just dead fish. Like more weird fish that we've never seen before. There's less mutation with radiation than is shown in pop science. There is mutation for sure. If a pregnant woman is exposed to high levels of radiation, what's literally happening to your body is when it passes through your body, because it's so high energy, it hits your DNA and it knocks all those T's and C's and G's, and now they don't make sense, and your body can no longer replicate the way it's supposed to, and that's what cancer is. It says, hey, go crazy and grow whatever you want, and that's what happens. It's not realistically going to give anybody superpowers or anything crazy like that, unless cancer is a superpower, which I don't think it is, just so you know. All right, here we go. Sorry if that's depressing. That was not my intent. Okay, so here we go. What I want to know is two things. First, and we'll do two questions. Part one, how much will remain in, give me an absurdly long amount of time for humans. 15,672 years. Okay. Yep, I'm cool with it. I was thinking 100 grand is what I would have gone with, but I'm cool with this number. It's all the same. Now, real quickly, we are going to estimate this before we do anything else. Is this quite a half-life? How long is one half-life for plutonium? 24,100. This is less than a half-life, right? Which means if I haven't even gone one full half-life, I should see more than half of it left. So in my head, I have no idea what this number is. It was just thrown out there. Between 5 and 10 for sure. Probably like, I don't know, that's more than half of a half-life because 12,000 is roughly half. So I don't know. Yeah, I'd probably say like 6.8 to 7.2, somewhere in there. I have no idea. I haven't done the calculation. But we're going to do it. So here we are. We want to know how much is left after this much time. And does this feel like the exact same accounting problem that we were doing yesterday? Not what I was expecting. I was thinking no, because it feels very different, but it's not mathematically. Check it out. We're going to use some different letters, but nothing has to change. Yesterday's formula, I'm going to write it up here, and we're going to see if just changing the letters doesn't throw us off too much. When we wrote the account balance at time t, what kind of deal were we hoping for? Pretty good. All right, I'm cool with that. What's P? And what is, ooh, I liked your word, Dolan, but I liked your word also, everybody else. Principal, what's a principal of something? The initial amount. Do we have an initial amount of plutonium? Okay, so that lines up. E just exists. If it decays at a very particular amount or a very particular time, there must be a rate associated with it. And do we have a time? We have like everything that we need. The last little part, that only part I care about, this is the formula that we use for which, not the only part, I'm sorry, but this is the formula for what kind of compounding interest? Continuously. Do you think decay in the natural world happens continuously, or is it once a month some of it shoots out? Of course it's continuous, right? This model matches perfectly with this exact same situation. Now, what I typically do is I would change the way that we write this. We could use A of t all the same. Not normally. What do you want to use A? Do you want to call it something else? Doesn't really matter what variables we pick as long as we can sort what they are. I'm going to let y be the variable that I choose, and I'll switch to a color that's not always my thinking color. This is the amount at time t, y. And I'll even call it y of t if we want to. Equals, I'm just going to use A right now as my initial amount. E to the, we could use R. Does it matter really what letter I use? Is this the same formula here, except echt doesn't sound as good as pert? Like, it's the exact same formula, I'm just changing the letters. Okay, this one would represent the what amount? So let's just see what shakes out. What is our initial amount of plutonium? 10 pounds. So here's 10 pounds. E, and this is the hardest part. If I need to know the rate that it decays at, it's hard to tell. When we talk about rate, it's per century, right? Per cent, per 100. This number is going to be huge because it's not really a per 100 sort of situation. If I need to know that every year, how much does it go? Do you guys agree it's 1/24,100th? If it takes 24,100 years for a whole half-life, then 1 year is 1/24,100th. Okay, so I don't want to actually calculate out the rate, but I think I can reason it out that we can probably just simply use 1/24,100. And it's just so I don't have to do the calculation. That's my rate. This is how much it decays per year. And how many years are we going to let this run for? 15,672. Okay, now I'm at the very bottom of my screen, and I should have plugged in y of, what are we plugging in for time? So I'm not going to make it say it again. I'm just going to plug it in here. This is, what is the amount y that's left after 15,672 years? On your calculators, we are going to do an approximation. We will go to 10 thousandths unless otherwise specified. That is 4 decimal places. My guess was 6.8 to 7.2. I have no idea what the actual number is. And Matilda, after getting an answer, you are going to miss a little bit of homework time, but if you're willing to sacrifice that to go help Padish. Cool. I'll let you go here in just a moment. So I'm very hopeful that we get an amount between 19 doesn't make sense. We got 19? Interesting. Where? Ooh. Check it out. I love it. Say it. Do we need growth or do we need decay? So what do you think we should do to this? Instead of a positive rate, let's change it to a negative. Good call. It took a second to find it, but we got it. Nice catch. $5.21. Okay, so again, my estimate is way off. 5.21. We agree with that? 21 what? 5.2. We'll go to 10 thousandths. 181. 89. Thank you. Okay, we have a lovely, wonderful approximation at this point. Are we done? Or what should we do if we have a very specific contextual problem like this? Pounds. So I'm not going to write the whole sentence as long as we can all say it. I'll trust that you guys can write it if needed. After 15,672 years, there are 5.2189 pounds of plutonium-239 remaining. Okay, now as we deal with these things are awesome. We reached out to a little bit different of a model here that I like way more than the other alternative. Okay, I'm fine with this model if you guys are. If you don't want to see the other one, or if you want to see the other one, we can also look at it, because I jumped ahead because I was excited to talk about all this stuff. Feel okay with it? All right. So what if I said how much is left in 200,000 years? Could you tell me? What would you plug in instead? Instead of 15,672, we would just have to plug in what? 200,000 if you didn't remember the number. Yep. Cool. All right. Do we have to do that? All right. Sweet. Well, I'm good with that. You guys get the next 20 minutes to work through a few things. Do we have 3.1.1? Oh, fantastic. All right. How many of you guys are going to go to the games tonight? You better. You guys got banned? All right. So you will need calculators, just so you guys know. Not for the games tonight, but for your homework. Cool. So I'll put the homework up over here. And let's see. Today is the 6th. Yeah. All right. So homework for today is going to be homework 3.1.2. And you will find this waiting on page, I assume it's 209. Page 209. And I want you guys to do problems 51 through 54. I'm going to give you a super short assignment. Or not. We'll see. I'm just messing with you. 68? Yep, and we're going to get to see the other version of this. But we'll do 69 there also. We used E because it's continuous today. When you look at the model that they give you on problem number 69, which is nuclear stuff, you'll see a slightly different model. I'm going to ask you why they used a different model, but I'll let you guys, I'll ask you about that. That's it. All right, appreciate you guys. Everybody have a wonderful, just kidding. Matilda, you have a wonderful day. I want everybody to have a wonderful day, but it was trying to say goodbye to everybody.